So good afternoon, everyone, and thank you for coming. I just like to show you my actual state, the actual state of my work with Jeremy Zechar, Valentin Gischig, Dimitrios Karvounis, and Stefan Wiemer in the Swiss Seismological Service. So the geothermal energy is getting more and more important in Switzerland since it has a great potential for future electricity generation. But we always have to face with the problem of induced seismicity since it poses hazard on infrastructure and the people living nearby. So it is essential to have a control on this seismicity. The existing warning systems are static and they do not account for the aleatory behavior of the seismicity. So we'd like to improve these warning systems, and what we'd like to do is forecast seismicity. And in order to improve the warning systems and develop a new tool, which would be the advanced traffic light system, this would be an on-site, near real-time decision-making tool. This is not a new idea. I just like to show you where we are now in this big work. So as I mentioned, we'd like to forecast seismicity, and it's already quite well established how can we do modeling and testing forecasting by the collaboratory for study of earthquake predictability, so the CSEP community. They developed 4 pillars, so the data, the model, testing, and the application. So as I mentioned, they used regional natural seismicity, and they used models which are mainly based on stochastic considerations. They used hybrid models as well, where they consider models or data coming from multiple sources. So for instance, not only seismicity, but GPS data as well. For the testing, they are interested in 3 different things. The first is the number of earthquakes for a given period, time period, the spatial, and the magnitude distribution. These are the consistency tests. For have a ranking of models, they consider a reference model, and they pairwise compare the models with respect to the reference model. And all these things to do on operational earthquake forecasting, which is still a huge challenge. But what we can do is to use this framework for induced seismicity modeling. And what we introduce here is our data from geothermal energy. So we have couple of cubic kilometers, or even smaller scale, which can be, so the data can come from underground lab experiments. Our models are classified into 3 different groups. First is stochastic models. I'm sorry. The second, where we try to model underlying physical processes, so physics-based, and the hybrid models where we try to merge stochastic and physics-based considerations. For the testing, we use exactly the same test as the CSEP community has already developed, and this gives us already a good bed for model development. We can know where our forecast and why it failed with the testing, and we can come back and make the models better. So everything is to develop this advanced traffic light system. So we'd like to react on not only occurred earthquakes, but potentially foreseen earthquakes as well. So I'd like to show you what we've done in the last month. As you can see here, our data is the Basel 2006 project. You can see the seismicity colored according to magnitude, and we used also flow rate data and wellhead pressure. So the models that we used, there are 2 models. Both are hybrid models. They seem to be the most suitable for near real-time assessment. The SIS model stands for Shapiro in space, since the number of events calculated based on the seismogenic index for the injection period. And for the second part of this time window, which is the post-injection period, we used a simple seismicity decay. What is new in this model is the spatial component. There are two main branches. So at first, we put a reservoir around the well tip and spatially equally distributed the seismicity rate all over this reservoir. This gives us the spatially uniform model. And the second is the so-called smooth seismicity branch, where we use a learning period and we take the earthquakes occur during this learning period. We put a 3D Gaussian kernel around each earthquakes. We sum up the contribution and normalize to get a 3D probability density function. And this can give us a good approximation where future earthquakes can occur. Here you can see some sub-branches. I won't talk about these in this talk. These are just temporal weighting that we added on top of the smooth seismicity. I will talk about this green and the uniform model in the next slides. So the second model is the high psi model, which is the hydraulics and seismicity. At the first part of the model, we invert for the pressure curve with irreversible permeability enhancement with a 1D radial symmetric flow model. And in the second part, we use the calculated pressure evolution in the reservoir to trigger randomly placed seeds in the reservoir. So we have 1,000 synthetic catalogs that we generate with this model. What we do for the testing is we are interested in the consistency. So we take a learning period, we educate our model, so we calibrate all parameters for this period, and then we forecast for the next 6 hours. Then we take a 6-hour step, and then we recalibrate all the parameters, and then we forecast for the following 6 hours. In terms of space, we are interested in the spatial distribution. So we put a 4 by 4 by 4 kilometer reservoir cube around the well tip, and we divide into 200 by 200 by 200 meter voxels. And we'd like to know what are the seismicity rate in each voxel. Since we consider the seismicity occurrence as a Poissonian process, we can use the Poissonian log likelihood, joint log likelihood, to evaluate the spatial distribution of the models. In terms of magnitude, we are interested in if the forecast earthquakes follow the Gutenberg-Richter law. I won't talk about this part in this presentation. I will focus on the number and the space test. In order to compare and have a ranking of the models with respect to a reference model, we use the so-called information gain per earthquake, where actually it's a pairwise comparison of model A and model B. We take the voxels where earthquake occurred, and we see which seismicity rate is higher, and then the winner is where the higher seismicity rate is in the voxel, and then we take the mean. So I just like to show you some preliminary results. Here you can see the CIS and the high psi model in terms of number of earthquakes per 6 hours and the time evolution. So at first glance, you can see that most of the time these models capture quite well what is the number of earthquakes for the next 6 hours. However, there are some points or periods which are crucial, and I highlighted them with red dots. And one moment is really crucial is the shut-in. So this is the injection period, this is the post-injection period, and around the shut-in you can see that there are some red dots where the model over or under predicts the number of earthquakes. Another thing is what we can see here is the late post-injection period. For the CIS model, the model systematically over-predicts the number of earthquakes. However, the high psi model during this late post-injection period captures quite well the number of earthquakes. Going to the spatial distribution, so here you can see the joint log likelihood on the y-axis in terms of elapsed days, and we consider each 6-hour experiment individually. In this axis, the closer we are to the zero, the better we are. And here you can see the spatial uniform model with gray, light green denote the high psi model, and the dark one is the smooth seismicity model. So first, you can see that both models are better than the spatially uniform model most of the cases. And an additional thing that I want to highlight is that during the stimulation, the smooth seismicity model is performing better. However, at the late period, the high psi model is getting closer to the zero. It means that better in spatial distribution. So not only in number, but in the spatial test as well, it's getting better by the end of the time window. If I'd like to rank the models, so we'd like to see what is the evolution of the information gain, the cumulative information gain. The reference model is the spatial uniform model. The color code is still the same, light green for high psi and the dark green for the smooth seismicity model. And you can see that at first it seems to be that the high psi is a little bit bigger, a little bit better than the smooth seismicity model. However, from day 2 on till day 6, it really decreases in terms of information gain, and finally it cannot really recover. And by the end of the time window, the smooth seismicity model won the competition. So, coming to the conclusion, you've seen that we'd like to develop an operational seismicity forecasting in deep geothermal systems, but for the moment we have more questions than answers. So actually, for instance, does the ranking change for longer forecast periods? For the moment we took only 6-hour forecast periods, but what can happen for longer periods, for instance for 24 hours or even longer periods? And naturally comes the second question, which is how to test for longer forecast periods that overlap. So for instance, I'd like to forecast for 24 hours, but I want to update it in 6 hours. So how can we calculate the information gain, for instance, when these forecast periods are not independent? And for the third question, for instance, would the combination of models give better results or not? So we are quite interested in, and I'm really open for discussion if you have still time and stay. Thank you for your attention with this.
Thank you, Esther. We have time for questions.
Can you repeat the question? That was very interesting. Looks like your model works fairly well for, at least for small scale applications. Do you think that the same methodology can be extended to, and you touched on this briefly in questions, much larger time scales and much larger sort of ranges? So sort of the situation where we have wastewater injection wells and reduced seismicity maybe 10 kilometers from a fault over a period of several years.
Okay, so the question was that is it possible to make bigger time windows and in space as well? I think it's possible. It's still an undergoing thing that we, as you've seen my questions, but definitely we will do more data and more, probably more physics-based model we'd like to integrate into this framework, and hopefully we can get results even for overlapping forecast periods. This would be really important for operational purposes.
Thank you very much.